Okay, so welcome back. So we're talking about decision theory, and in this first section, we're going to be talking about decision theory for the case when we were trying to minimize the misclassification rate. So trying to make the fewest mistakes possible. Now, a subtle point at the very beginning that we should discuss is that in decision theory, you always have to come with a goal or a target or a criterion. So you can't make decisions within this framework unless you know what you're trying to optimize. So you know the probabilities themselves, your uncertainty itself isn't going to tell you what to do. You have to tell it. You have to know or arrive with some notion of the cost of decisions or something that you're trying to optimize relative to those uncertainties. And then often it can be quite simple to then come up with a decision. But in some sense, the hardest part can be to decide, okay, what makes a good decision and what makes a bad decision, and trying to quantify that. Once you've quantified that, then you can then combine it with the probabilities, as we'll see here and in subsequent sections, to make the decision that you want, the best decision. Okay, so in this particular section, we've decided, so someone has told us that the goal is to make, let me switch to the laser pointer here, as few misclassifications as possible. So we have our data points, and we're going to assign them to one of a few classes. So going in the previous example, it's going to be the cancerous or non-cancerous. And our simple aim is to just say make as few mistakes as possible. So assign as few people who actually have cancer to the non-cancerous category and vice versa. So that's going to amount to coming up with this rule that assigns each value of x, so for example those images, to one of the available classes. So whether does this image map to what we think is a person with cancer or not. And so this is going to then divide the input space, so that's the space where x lives, into these decision regions, because every point is going to be assigned to a single class. Into regions RK, so we'll see RK below. These are decision regions such that all points in RK are assigned to the class CK. So you're going to take the space, split it up by where you're assigning each of the points within a region too. And the boundaries are called the decision boundaries or the decision surfaces. And yeah, an important point is that decision regions don't need to be continuous. So you don't have to have kind of just one solid, connected block for one decision. They could be separate. There could be, there could be a chunk here that corresponds to, person having cancer, and then another types of images that are disconnected from the first also corresponding. Okay, so that's going to be the setup. Now, and let's just consider kind of the two class case. So we're just trying to think about cancerous versus non-cancerous. So a mistake occurs when an input vector belonging to class C1 is assigned to class C2, or vice versa. Okay, so here is now the probability of a mistake, and it has two parts. It's the probability of x belonging to R1. So we've said, let's say, cancerous, where actually x came from the non-cancerous case, plus the other probability. And so we can write that in terms of these two integrals. So this is, we're going to integrate x over all of region 1. So we're going to integrate this probability of x from class 2 over region 1, and the probability of x coming from class 1 over region 2. And that's going to be our mistake probability. So that's for a given set, given R1 and R2. So the whole, the decision theory is going to tell us how to determine R1 and R2. So how to assign x to R1 and R2. So the game is going to be to determine our rule that assigns x to one of these regions so as to minimize this number. So now the way we're going to discuss this, so he mentions it, he talks about it in this next sentence as, clearly to minimize mistakes, we should arrange x so it is assigned to whichever class has a smaller value of the integrand. Okay, so we're going to discuss what that means in two ways. So we're going to do it first kind of algebraically. So I'm not a big fan of this. This expression is correct, but we'll write it in a different way, which I think is a little bit more clear. And then we'll also talk about it graphically. He's got a really nice graph that shows it in a simple case, and we'll see how to make the decision based on what's happening in that graph. So let's first go over this. So how, based on if you want to minimize probability of mistakes, how should we decide where to assign, which class we should assign a given x to? So So we're going to do this on a new page. So I'm going to switch now. So let's go down to, okay, so we've got, let's write our probability of a mistake. So probability of a mistake. And he's written it as, and he's correct, as integrating over R1. So this is going to be dx over R1. Probability of x and C2 plus R2 dx px and C1. Okay, so, and the whole we want to kind of minimize. So now, goal is to minimize over, let's say, R1 and R2, P mistake. And I think a clearer way to write the same thing is to actually have the rules be explicit. So we're going to write the exact same integral in a slightly different way, so that we still have the probability of our mistakes, but now we're going to integrate over all of space. And we're going to say, well, we're going to count the probability of x coming from let's say the non-cancerous case as a mistake if our rule, so we're going to have a rule called R1 of x, assigns it to class 1 plus P of x C1, so a data point coming from the other category, which we then mistakenly assign to the opposite. So what are these R1 and R1 and R2x? So R1x is just going to be a binary. It's going to be a binary value, which is going to stand for assigning x to class 1 when it's coming. It's just going to mean x is being assigned to class 1. And R2 of x is also in 0, 1, but it's going to be defined as 1 minus R1 of x. So it's just going to be the opposite thing. If R1 of x is 1, then R2 of x is 0. So they're not separate. It's about the same. So now let's write P of mistake again. So again, integrating over all of space. And now we have P of x C2 R1 of x, just like before, times 1 minus R1 of x. Okay, so let's switch the laser pointer here. So whenever this is 1, that's going to be 0. And whenever this is 0, that's going to be 1. Okay, so now the game is going to be, so now our game is going to be to minimize, so minimize over R1, of x. So we have this kind of function, this rule, P of mistake. And just the important observation is that we can just do this separately at every single point. So P of x, P of x C2, P of x C1 are given, and we're just free to choose R1 of x to minimize each one of these terms as we integrate over all of space. So how should we do that minimization? So it seems so now if we consider a single point, well, R1 of x should be chosen so that it picks the smaller of P of x, so that we include the smaller of P of x C2 or P of x C1, right? Because we have two choices for R1 of x, either it's 0 or it's 1. If it's 0, well then P of x C1 gets chosen. If it's 1, well this becomes 0 and P of x C2 gets chosen. So it seems like, so just from that kind of reasoning, we should pick R1 of x should equal to 1, if P of x C2 is less than P of x C1. Right? And that just comes directly from trying to minimize this sum. So if R1 is basically a switch, and we wanted to switch in such a way that it picks the smaller of, so it's 1 if P of x C2 is smaller than P of x C1, and vice versa. So in other words, we can just say, so if this is the case, so you can say, in other words, R1 of x is equal to this decision P of x C1 is greater than P of x C2. And now we can use, if we use Bayes' rule, we can just write this as P of C1 given x, P of x greater than P of C2 given x, P of x. And these guys cancel out. So we arrive at the intuitive conclusion that R1 of x should equal 1 if P of C1 of x is greater than P of C2 of x and is 0, otherwise. So that's the decision rule, and we just got that directly from just minimizing this integral about the of the mistakes, at every single point, and it gives us the very natural decision rule that we should assign a point to a region if the probability of x coming from that region is higher than the opposite situation. Okay, cool. So that was the kind of maybe an algebraic or an algebraic approach to the solution. I think there's actually, so he actually also provides a really interesting and really, I think, cool graphical representation of the same situation that we should talk about. It also tells you kind of where, again, where you should pick the decision boundary and what happens when you pick it incorrectly. So let's talk about that now. So I've actually cut and pasted down here because we're going to be looking at two different cases of it. Okay, so what do we have here? So here we've got the probability, the joint probabilities of the two, the class becomes kind of difficult, but let's call them classes, so C1 and C2. So here's the data, the probability of x from the first class, and the joint probability of x from the second class. And in this figure right now, we've picked the decision boundary at this x hat location. So everything on this side, we're on the left side we're assigning to region 1, and everything on that side we're assigning to region 2. So now we want to see, okay, where are our mistakes happening? So there's going to be kind of the mistakes are going to be coming from two sources, right? They're going to be either coming from this distribution or this distribution. And now we can see, and he's colored them differently because there's these regions are going to have interesting properties. So first, this region here, these errors, these are going to be the errors that are going to be contributed from class 1 being misclassified as class and being put in region 2. So you see that this is just the area of P of x C1 that's on the other side. We want all of the class 1 points to be in region 1, but these are the ones that are in region 2. So that's one source of error. And then the other source of error is just the opposite case. So that is the points that are coming from class 2 but are being put into region 1. And those points are the sum of the red regions and the green regions here. So these are just all the points that are coming from this distribution but are being put on the left side, so being assigned to region 1. Now the interesting thing, and the reason why they've been kind of colored differently, is what happens if you move the decision boundary. And it turns out that when you move the decision boundary, the contribution of the mistakes due to the blue and green regions stays the same. So the only thing that changes is this red region. And the reason, and you essentially set your optimal decision boundary where that red region is going to 0. So I thought we could kind of look at that by considering a different decision boundary, a different decision location, and seeing what happens to these regions. So that's what I've drawn down here, and I've colored in I've colored in the points white so we can recolor them together to understand what's happening. Okay, so in this particular setting, we've moved the decision boundary. So the decision boundary is now this line over here, and let's see what happens. So let's see where the mistakes are going to be coming from. So remember we started with the blue region before, which were the points coming from class 1 that were now being assigned to class 2. So all of those points, so let's just color those in. So you see, so we had the previous set, that were being previously misclassified, they're still being misclassified because we've shifted the decision boundary to the left. But now we actually have an additional set of misclassifications of points from decision 1. So remember previously, these points were actually being correctly classified if they came from region 1, but they were getting misclassified if they came from class 2. However, in this case, they're actually, because the decision boundary is moved, all these misclassifications are being contributed by points from class 1. So these are all misclassifications here. And we still have these ones as well being misclassified, all coming from class 1. And now we have a new red group. So this is additional points that are being misclassified from class 1. So in the previous example, the red region was points that were coming from class 2 that were misclassified. But now actually things have really improved for class 2, and most of the misclassifications are coming from class 1. So the only there's this tiny little toe of misclassifications that are coming from class 2. So these are the points that were class 2 that are now on the wrong side of the decision boundary. Now, so because we kind of moved the decision boundary to the left, most of the points from class 2 are now being correctly classified, but now we're getting a lot of misclassifications from class 1. Now the point of this exercise was for you to observe that actually the contribution, the sum of the blue region here and the green region have stayed the same. So previously, we had this area. Well, now it's exactly the same. Maybe the source of the errors has changed, but it's exactly the same total contribution to the mistakes. And now what's changed is this red region. So this red region is now being contributed from class 1, some points from class 1 that are being misclassified into class 2. So I think based on this visual representation, it should be clear that the sum of the green and the blue regions, they actually stay the same. And what changes is just this area of the red region. So we should choose our decision boundary at the location where that red region is 0, and that's exactly at this location. So you can see that if we set our decision boundary to x0, which is at this location here, then all we have is these kind of unavoidable errors due to the overlap. And we don't have any of this red region contributing. So we just get the minimum error possible. And this boundary exactly corresponds to our decision rule that says assign a point to a class if its posterior probability is larger. So where you can see, so here, the points are being assigned to the class 1 when this probability is larger than that one, and being assigned to class 2 when this probability is larger than that one. So that was just kind of a graphical representation of the decision process and where to set the decision boundary when your whole aim is to minimize the misclassification rate or the number of mistakes you're making. So that was that. Okay, so now just going back, and then we just finish off this section by just talking about what happens when there are k classes, and it's just an obvious extension. In this particular case, he's going to look at the probability of correct because it's a bit easier when you have multiple classes. So this is now the sum over all of the different regions of the probability of x coming from that region and it being in that in that class. Keep getting the classes and regions mixed up, but hopefully you know what I mean. And so it's just, again, it's this integral, but now split up over our different regions. And now you can imagine just doing the same kind of algebraic computation we did of having an R1 corresponding to one of the classes, then R2 corresponding to the second class, essentially having a one-hot encoding, and then trying to assign R1 in such a way that this integral is largest. And it's quite clear in that case that you should assign R1, or R2 or RK in such a way to the class which has the largest posterior probability. So in this particular setting, so in summary, when your whole point is just to minimize the misclassification rate, the way you should assign a point to a region is by assigning it to the class that has the highest posterior probability. And that's kind of what decision theory tells you. When you have arrived with your joint probability over points and classes, and that with the criterion that what you're trying to minimize is your misclassification rate. Okay, so I think that's about it for this section. And next time we're going to talk about having a different goal that you're trying to optimize, which is the expected loss. See you then.